Hi guys, how is it going? So, a quick question. As a Spark developer, have you ever used sorting technique before? If you used it, what sorting range did you use? When I first learned about sorting and when I first implemented it, I had to go with the number of executor calls within the cluster. So you can use number of executor calls, but if that is not the right number, that can also create another problem called mini-skew. So this video is going to be about using the right sorting range for our sorting optimization technique implementation in Spark. So right, let's get started with how Spark basically assigned record to specific partition. So when you submit a Spark job, Spark does shuffling across the partitions within the executors. Now in the latest version of Spark, there is a method called adaptive query execution, which sort of like help with these things. But normally Spark does shufflings across the executor, right? But when Spark does shuffling, it needs to decide which partition a specific record needs to go to, right? In the background, Spark has the join key, right? So maybe you are joining by user ID or customer ID. So Spark use hashing technique to hash the key and then calculate which partition that record should go to, right? So this basically how Spark determine which record should go to which partition, right? So there's a function called hash that Spark use, and basically it calculates the modulus of that, the results of that hash with the number of partitions within a cluster. By default, Spark use a throughput partition of 200, right? But you can set the number of partitions within your cluster. You can set it to the number of cores within your cluster. So basically, by setting it, you basically sort of like enable core alignment, right? Now, so say for example, you have an input data, a simple input data, and you have a data that has the key of A, and that record exists basically appear 6 times within the table, right, or data frame, and you have another key that exists like 3 times. So the key ID is B in this case, and you have another one that has that exists 2 times, and the other 2 exist one time each, right? So you can see the record with key A or ID of A exists 6 times. So that is basically what you call hotkey, right? So the key A is basically hotkey because it appeared the most within the table or within the data sets. Now, how does Spark assign this record to its partition? So as I mentioned earlier, Spark uses hash key. Basically, it put the key, like key A, you put it in hash function, basically convert it to number, right? And when it does convert it to number, it uses modulus and it gets the number of partitions within the cluster. Now, say for example, the number of partitions within your cluster is 4. So the number of partitions can be set by using spark.sql.sophos.partitions. So the number of partitions is set to 4, right? So now when you calculate hash key A modulus 4, you get 1. And you calculate hash key B modulus 4, you get 1. Now you see, so that 1 here is basically the partition. So you can think of partition as a bucket. So if you have 4 partitions, you have 4 buckets, right? So this is bucket 1, and this is also bucket 1. If you hash key C and get modulus 4, you get partition 3. So C record go to partition 3, and D record go to partition 2, and E record go to partition 1. So you can see what is happening now. All of A record are going to partition 1. No, the all of C record are going to partition 1, and all of E record are going to partition 1 as well. So this is the partition and bucket analogy. So you can think of as partition as bucket. Each row K is hashed and placed into one bucket partition, right? So you see now all of A record are going to partition the bucket 1, B bucket 1 as well, and E are going to bucket 1, and D go into bucket 2, as you can see here, and C go into bucket 3. So it's like bucket 1 already has 10 record. Bucket 2 has 1 record, and bucket 3, partition 3, has 2 records. Now bucket 0 is empty. Now imagine this is a hundreds of millions of data sets, and then you are going to end up with millions of records in bucket 1, and bucket 0 may have little to less record, very few, right? And bucket 2 we have few record. So after bucket 0, bucket 2, and bucket 3 finish their work, their task, so there will be a particular executor that is basically processing the data within this partition. So after they finish their job, they are going to say idle because there is nothing else for them to work on. But bucket 1 is going to keep working. In partition 1, the executor or worker name responsible for partition 1 is going to get overloaded, and it's going to keep working, and that is when you end up with a data taking a job taking more than 1 hour. And when you look into your Spark UI, you see that a specific job is taking huge amounts of time, and a specific executor is trying to keep up, try to execute process the data, and it's taking a long time. Sometimes you may end up with out of memory issue. So this is a bad thing in Spark, and that's why this is what you call skew. Now let me show you an example of what I just explained. Here I've set the number of partition to 10 because that is actually the number of cores that exist in my system. So I just set the number of cores the number of software partition to 10. So now you can see I've created some data frame here, and I've joined 2 data frames together. The partition here is 10, and one thing you should notice here is partition 7 has got just 1 record in it, and the rest of the record go to partition 9. This is basically without sorting, right? So that is how sorting, that is how data skew managed to happen. So you can see partition 9 has all of these 3 records, and partition 7 just have 1 record. So, and that is also a case whereby you are just running a small data frame. You don't need to have huge amounts of software, so you can reduce the number of software in this case to 4 instead of the number of partition to 4 instead of 10. So without sorting, this is what your partition will look like, right? With sorting, we use basically sort of composite key, right? So we when we have A and we have key A, key D, key C, and so on. Now, to enable even distribution of the record across the partitions, we need to basically we need to create a subset, multiple subsets of the key or multiple subkeys. And to create multiple subkey, basically we need to sort of have a sort range, the range of number that we need to use and basically append that number to the original key. And that is why we have A0, A1, A2, A3. Say for example, our sort range is 4, then we have A0 to A3, right? Now, if our calculation is correct, we can Spark will basically allow these 4 keys to be distributed across the partitions or buckets. So basically, this enable parallelism and improve the job performance. Now, with that being said, there is a terminology called mini-skew. So how does mini-skew happen? Mini-skew happen when you perform your sorting. During your sorting, basically you want to allow the data to be distributed across the partitions. But there are cases where the data are not as evenly distributed as we expected. There are some more partition, more data or more record going to the same partitions compared to others. So this is where mini-skew, and this is where it's important to know the right sort range you need to use. So if your sort range is also the same factor as the number of partition, right, that can create the basically what we call mini-skew, right? So you can see here when you use hash key, when you use sort range of 4, right? So basically you have hash key from 0 to 3, right here. So when you Spark basically calculates which record should go to which partition, you can see here already partition 1 already has 2 records, whereas partition 2 has 1 record and partition 7 has 1 record. So example is this. So if you do hash key 0 modulus 8, you get 1. For modulus 2 key 1, you get 7. For key 2, you get 2, and for key 3, you get 1 as well. So you have 2 records going to partition 1, and you have 1 record going to partition 2, partition 7, and another record going to partition 2. Now remember, you've got 8 partitions, right? So you end up with 4 other partitions empty, 4 empty other partitions. So as you can see here, the first record going in here, second record going to P2, P3, P4, P5, P6 are empty, P3 going to P7. So all of the executors responsible for this are not doing as much work as the partition 1 is doing. So this is where mini-skew happen, and the reason for this, as I mentioned earlier, is when the sort range is the same factor, is the prime factor of 8. So if you say 8, right, what is the factor of 8? So the factor of 8 are 2, 4, and 8, 1. If I'm correct. The prime factor of 4 is like 8 is like 2 and 4. So you see 4 is prime factor of 8. So if you divide 4 by 8, if you say 4 modulus 8 or 8 modulus 4, I mean, it's going to give you 0. So there's not going to be remainder. That is why you need a prime factor. That is where prime factor technique comes in. So to avoid mini-skew when you are using sorting optimization technique, always look for prime factor and prime number, right? So for example, you've got a partition of 8 If you use 5, that is okay, but you want your sort range to be equal to or greater than the number of partitions within the cluster. And also the number of partitions, I'm thinking in a case where it's aligned with the number of cores within the cluster. So for example, if you're working in a big environment where you've got maybe more than 200 cores or 200 cores, right? And so that is the number of software partitions within the cluster. Now, if you need to apply sorting technique, don't go for 200 because 200 is it's not a prime number. So go for maybe 211 as a prime number. So 211 is not a prime, it's not a factor of 200, which is the number of partitions within the cluster. 100 is a factor of 200. You can divide 100 by 200. You can divide, I believe, maybe 14 by 200, 50 by 200, 200 by 200. So you cannot divide 211 by 200 without any remainder. So use that as your prime factor. In that case, your data will be more evenly distributed when you use a sorting technique. So it won't create any mini-skew. I'm going to show you some examples. So I've created some scenario here and sort of like created a data frame worth of 50 million record. So the hotkey share from that data frame is basically 40%. So there are 40% of data that belong to the hotkey. So that's why you have 0.40. So this is basically the skew ratio. When you want to calculate the skew ratio before the for the sorting, initial sorting, that is like the total number of records that belong to the hotkey divided by total number of records across the whole table or the whole data set. That gives you this 40%. Now the software partition I've selected here is 200. Note this is going to take more time because there's going to be a lot of software and my PC only have 10 cores. So, but I'm just using this for example. And I've created a scenario here where I've created the data frame and basically selected use different type range of sorts. Sort range. So there's a 40, 50, 100. So some of these are basically a factor of 200 because I mentioned earlier that you need to make sure that your sorting range is not a factor of the number of partition, right? So I've sort of like created some scenario here, and this is where I basically use sort and apply the sorting technique here. So for this data frame, I've basically used rand multiplied by the sort range, and so the rand is basically going to make sure that the number is going to be from 0 to the number of sort range. So 0 to probably say for example is 40, so basically we do to 39, something like that. And the so after that I basically created the sort key column, then concatenate the key, the column key with the sort. So this is where how you create the composite key, basically create a sub key for the sorting technique. Note, if you are joining two tables together, maybe you join a fact table dimension table, you need to explode the sort range within the dimension table for your joining. But what I'm doing here is basically use aggregates. I'm not joining table here. I'm just using group by then do some aggregates. So after I run this code, basically the number of the factor of 200, these are the factor of 200, 40, 50, 100, 200. So this is there's part of the code that's checking whether the sort range I'm using is a prime or not. So the first number is not a prime number. I'm using 40, but it's a factor of 200 as well. So this take the skew ratio calculator after. So if you divide that the hot key occurrence divided by the average other key occurrence, you get the ratio of the key skew. So the closer the skew is to 1, the better the distribution of the data across the partition. So if it goes above 1, the distribution is not good at all. If it's like 1, if it's like 1.23, 1.30, 1.14, that means it's not as evenly distributed as expected. But if it's like 1.0 something, it's more evenly distributed. So this is what we are getting here. So for 40, you can see it's 1.28. It's not well distributed. So for 50 is still a factor of a number of partitions, which is 200. This is 1.25. We've got 1.14 here. So when we go to the prime, this is prime. It's still less than the 200, but it's still a prime number. So this is okay. So it's coming down now, right? So when you get to 199, so 199, if you use modulus 199 against the number of partitions, you get 1. And for 211, you get 200. So this has reduced to 1.07. And this, you can go for this 223. This is a prime number, and the value is also greater than the number of partitions. So the way you select your sorting range, basically the sorting range has to be a prime number, and the sorting range also has to be equal to or greater than number of partitions within the cluster. So you see, and the time here is 4.63 compared to other ones, and it's 1.07. So this is 1.07, but the time is the elapsed time is 5.45. So this seems like a better option for our sorting range. So you can use this as your sorting range. Now I've changed things up a bit. So the number of records is still the same, but I've changed the number of software partition to 10 here. And then so based on that, if the number of software partition is 10, this is what you get. So 1, 2, 5, 10, basically the factors of 10. So I've basically used this range 2, 5, 7, 9, 11, 13, 17. So what you can see here, 2 is prime, 5 is a prime, 7 is a prime, 9 is not a prime. Only one is 10 is not prime. But you can see this sort of like has good skew ratio here, but it's not a prime. If you have like a way bigger data set and huge amounts of executors and calls, that can be a problem as well. You create a mini-skew. But moving forward, this is 11, it's a prime, but it's still, the skew ratio is still the same as this one. It's 1.04. And the time here is kind of more than this, but as I said, this is just in one computer in basically processing not huge data sets. And this is 104. And if you notice here, this is 1.30, and it's got 104 ratio, which is very closer to 1. So this is still better than this and that. But I think the previous example is way better. But as you can see here, the time elapsed time is very, very low compared to the previous example, and this is because we are using the amount of executors within our computer. We are basically not doing shuffling up and down across partitions. So if you're doing lots of shuffling, then it will end up your job will end up taking more time. But if you make sure that the number of partitions is equal to the number of cores in your cluster, that is still better than some huge amount of partitions, you know. So to go back to the key takeaway, you can think of partition as bucket. Spark uses bucket to distribute data, and in the background, Spark is using hash key modulus number of partitions to determine which record to go to which partition. And basically, skew happens when there are many records that goes into just one bucket in one partition compared to others. Now with sorting, you can basically use composite key or subkey to sort of like distribute the data more evenly across the partition. And like basically using a prime factor, you can prime number as your sort range, and that prime number should not be a factor of the number of partitions. You can basically avoid the issue of mini-skew, right? So that is another thing. So basically, using sorting optimization, you can better improve the performance of your application, utilize the resources very well. There won't be some executor sitting idle, not doing anything. And so with sorting, you can distribute the data across the executors, and all of them will be busy and try to get your job done and processed as fast as possible. So yeah, I think that is it for this video. Thank you for watching. Please don't forget to hit the like button, subscribe button, and leave a comment. If you want more video like this, leave a comment. Thank you. Have a lovely day and goodbye.